Hello, welcome back. We are rounding out our study or our introduction of differential equations by learning two new types of differential equations today, the logistic growth and Newton's law of cooling. In the last lesson, we talked about exponential growth, and the differential equation for exponential growth presented an assumption that growth just continues forever. The differential equation for logistic growth is this guy. dy dt equals ky, where k was a proportionality constant. And then its solution is y equals ce to the kt. Now we're going to talk about logistic growth, which is a bit different. Logistic growth describes a population in which there often exists some upper limit, L, past which growth can't occur. So it's not going to grow forever. There's a limit to it. The differential equation for logistic growth is dy dt equals ky times the quantity 1 minus y over L, or another format of that is dy dt equals k over L times y times the quantity L minus y. And its solution, as you can see, is P equals L divided by 1 plus A e to the negative kt. That's a lot of letters, isn't it? So let's look at this a little bit closer. This L here represents this top asymptote of the graph, the carrying capacity, or we could also call it the limit. And you'll notice in the middle of our graph is an inflection point, because prior to the inflection point, the growth rate is increasing. It's concave up. Past the inflection point, the growth rate is decreasing. It's concave down, which means right in the middle, where that inflection point is, that is the maximum growth rate, and it occurs when the y value is L divided by 2, or half the limit. So it's going to grow, 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 and then when it reaches half of its carrying capacity, the growth rate slows, which makes sense, doesn't it? So let's look at these two different differential equations. Actually, they're not different. They're the same thing. How do you get from one to another? Well, if you look at the top one, we take the top one and factor out a 1 over L. That's how you get to the bottom one. Also, I want you to notice that the variable of integration, the y here, in both variations of our differential equation, the y is twice on the right side of the formula. So be looking for that. If you're taking the AP Calculus BC exam, here's some possible logistic growth questions you might be asked. One, you could be asked to write or recognize either form of this differential equation here. You might be asked to identify the maximum population or the limit, or you might be asked to identify where or when the maximum growth rate occurs. With that in mind, let's look at this one. The number of antibodies, Y, in a patient's bloodstream at time t is increasing according to a logistical differential equation. Which of the following could be that differential equation? So look at those and see which one you think. Well, it would be E. E is a logistic growth differential equation. Let's look at the others real quick, though. A is, yeah, clearly not. That's just not going to work. That's actually an exponential growth equation. B, wow, it looks really close, but what's wrong with B? What's wrong with B is this t here and this t here. If this was a logistic growth equation, those would need to be y's. That's the wrong variable of integration. And then C, yeah, C is out. And then what's wrong with D? D and E are really close, but what are we missing? We're missing the variable of integration right there. Example 2. Let's get into this. The rate of change, dp dt, of the number of antelope on an island is modeled by the following differential equation. dp dt equals 50 over 134673 times p times the quantity 814 minus p. Wow. Let's just look at that real quick and see if we can identify some things. So based on our model of a differential equation, this 50 over 134,673, that's in the K over L position, okay? And then we have our variable of integration, and then 814 is L, and then our variable of integration again. Let's keep reading. At time t equals 0, the number of antelope on the island is 231 and is increasing at a rate of 50 antelope per day. At what value p does the graph of p of t have an inflection point? So at what value of p? That's essentially a y value, and the y value is going to be at half the limit. Well, what's the limit? The limit is 814 antelope. So when P is 407, there's going to be an inflection point on the graph. Now the second part of this question says, what is the limit as n approaches infinity of P prime of t? So n is approaching infinity, we're looking at end behavior, and we want the slope as n approaches infinity. Well, a logistic growth equation kind of goes like this, doesn't it? And we have our carrying capacity or our limit at the top. Well, as n approaches infinity, what's the slope? The slope is 0. P equals 814 is a horizontal asymptote. Let's try another one. The rate of change, dp dt, of the number of people in a mall is modeled by a logistic differential equation. The maximum number of people allowed in the mall is 2,000. At 10 a.m., the number of people in the mall is 200 and is increasing at a rate of 400 people per hour. Write a differential equation that models the situation. Okay, so I've got the two differential equation models down here. I like to work with the top one the most. So let's get a little sketch of what we're going to work with here. And let's fill in what we know. So let's read it again and start highlighting some of the things we know. So we have a rate of change, dp dt, of the number of people in a mall is modeled by a logistic differential equation. The maximum number of people allowed in the mall is 2,000. That's the limit. So let's put 2,000 in for L. At 10 a.m., the number of people in the mall is 200. So they're giving us a y value at the 10 a.m. time hack. So we'll put 200 in for y, and is increasing at a rate of 400 people per hour. Okay, so there's our rate. So the only thing we're missing here is a k. But we have enough information to solve for k. So let's clean this up a bit. We can divide both sides by 200 and then reduce this fraction a bit. Ooh, let's clean that up. So we have 2 equals k times 1 minus 1/10. So 2 equals k times 9/10. So k is 29ths. And now we can write our differential equation. dp dt equals 20 over 9. There's k, there's p, 1 minus p over 2,000, and that's our limit. You could have also done a different algebraic manipulation of that, perhaps if you prefer that second version of the differential equation. So we've covered exponential growth and decay, we've covered logistic growth, And the last differential equation I'm going to introduce you to is Newton's law of cooling. And this law states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and some fixed constant B, which is the temperature of the surrounding medium, like maybe the air temperature. So here we have the differential equation for Newton's law of cooling. dy dt equals K times the quantity Y minus B. And again, that B is the temperature of the surrounding medium. If you solve that differential equation, you get this solution, y equals AE to the KT plus B. Applications of this would be, well, heating and cooling objects. That's why it's called Newton's law of cooling. Falling objects approaching terminal velocity, or inside pressure approaching outside pressure. Let's check out some hot chocolate. A cup of hot cocoa cools at a rate of dH/dt equals negative 0.05 times the quantity H minus 75 degrees Fahrenheit per minute, where H represents the temperature of the hot cocoa and T is the time in minutes. If the cocoa was initially 160 degrees Fahrenheit, what will its temperature be 10 minutes later? Let's go ahead and solve this differential equation, shall we? So the first step would be separation of variables. Get all the T's and constants on one side and all the H stuff on the other. And then we can take the antiderivative of both sides. So we get the natural log of absolute value, H minus 75 equals negative 0.05t plus c. Don't forget your constant of integration. Now we can exponentiate both sides and then add 75 to both sides to isolate h. Now the last thing we're going to do is take this c, okay, and just pop it forward. And I showed you why we could do that in some of the previous videos. So we have h of t equals c e to the negative 0.05t plus 75. So we need to figure out what c is. So to do that, we're going to use the initial condition that they gave us, that h of 0 is 160. So we'll plug in 0 for t and 160 for h. And then e to the 0 is 1. So we've got c plus 75, so we can just subtract 75, from both sides. Good algebra skills there. And we've got c equals 85. Now we have our general model, and if we want to know the temperature of the hot chocolate 10 minutes later, then into T we can plug a 10. And 10 minutes later, our hot chocolate has cooled to 127 degrees Fahrenheit. All right, now this last problem we're going to work through was actually on the 2017 AP exam. There's all kinds of stuff going on with this one, so I like it. At time t equals 0, a boiled potato is taken from a pot on the stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies this differential equation, dH/dt equals negative 1/4 times the quantity h minus 27, where h of t is measured in degrees Celsius and h of 0 equals 91. Now notice, I just read that whole thing out loud. And that's an important thing to do because it slows you down and lets you really take in all of the information. Now, the first thing we're supposed to do is write an equation of a tangent line. Write an equation of a tangent line to the graph of h at time t equals 0. And then we're going to use this equation to approximate the internal temperature of the potato at time t equals 3. All right, in order to do an equation of a tangent line, we need two things. We need a point and we need a slope. They've given us an initial point of 0, 91. Now we need a slope. And the slope of our tangent line is going to equal the slope at the same time of our graph. What do we do with that? Well, slope and derivative, it's the same thing. So here's our slope formula. dH dt equals -1/4 h minus 27. And it's at time 0 that we're interested in. So at time 0, we know that the temperature of the potato is 91 degrees. So the slope at time 0 is -16. Well, with our point and with our slope, we can now write the equation of our tangent line. Then the temperature of the potato at time t equals 3 would be -16, and just plug in 3 plus 91 degrees. All right, use the second derivative to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature of the potato at time t equals 3. Okay, we need the second derivative. So the second derivative is just -1/4 dH dt using implicit differentiation. And we know what dH dt is, so let's go ahead and substitute that in there. And we can clean it up a bit. So we've got 1/16 times h minus 27. Well, back in the problem, it said the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0, which means this guy is never going to be negative. We have a positive double derivative, so the graph is concave up, which means our tangent line is an underestimate. Now the last part of this, they kind of changed the game on us here. It says for t less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies this differential equation, negative g minus 27 to the 2/3, where g of t is measured in degrees Celsius, and we have an initial condition that at 0 we have 91 degrees. Find an expression for g of t, and based on this model, what is the internal temperature of the potato at time t equals 3? All right, so let's just solve this guy. First, we'll do a separation of variables, okay? And then I'm gonna rewrite this so we are not in a fraction form. So we've got g minus 27 to the -2/3 dg, and on the other side we have a negative dt. Take the antiderivative of both sides. We get 3 times g minus 27 to the 1/3 equals -t plus c. And we'll pause a moment, shall we, and solve for c. So we've got our initial temperature of 91 at time t equals 0. So if we solve for that, we get c equals 12. Now let's go back over here and plug in 12 for c. And let's solve for g. So we need a g equals of some kind. So divide both sides by 3. And then to get rid of this fractional exponent here, we will cube both sides. All right, now we have our general model. And to figure out the temperature at time t equals 3, there we go, just plug in a -3, and you're done. So we should label this degrees Celsius. If you want to know exactly what all that is, it's 54 degrees. So that's the end of our unit on the introduction to differential equations. Lots of fun stuff to do with the 3 different types: exponential growth and decay, logistic growth, and Newton's law of cooling. Thanks for being here, and we'll see you in the next unit.